All right, welcome back. We'll come now to more of the computer vision aspects, namely seeded watershed segmentation and watershed segmentation. So seeded watershed segmentation means we need seeds and then we assign pixels to closest seeds based on minimax path costs. Now, here I have an example, a tiny image, 3 by 3 pixels, and the user wants to give 2 seeds. Let's say this is meant here to belong to the green class, and this pixel is meant to belong to the blue class. And now we want to partition this image somehow into green and blue, or foreground and background, or whatever the seeds are meant to indicate. And we have some edge weights estimated from a neural network or so. Now, we can create a minimum spanning tree problem as follows by introducing these extra nodes here. And these extra nodes are connected with an edge weight of 0 to the graph, and they're connected with an edge weight of 0 to a meta node. Now I can start my Prim's algorithm or Dijkstra's algorithm here and proceed along these cheapest edges. Excuse me. All right. And now what edges do I have available at this point? I have edge weights of 3 or 4 or 5. Or I have edge weights of 6, 7, and 8. So the cheapest edge at this point is 3, and I'm adding this one to my tree. Then a new edge becomes accessible with a weight of only 2, which I add here. Another one becomes accessible with a weight of only 1, which I'm adding there. And then in order of increasing cost, I add 4 and 5, now 6. I don't want to add, or I'm not going to add. There are 2 ways of arguing this. I could either say, because by doing so, that would create a loop. And to find or to understand if I have a loop, I could always use the union find data structure. Or by using the recipe I gave you earlier, well, the cumulative cost of reaching this node, the minimax cost of reaching my source here was 4, and to reach it along this route would make for a cost of 6 that would be more expensive, so I'm not going to add that edge. For the same reason, I'm not going to add this edge here, because that would have a cost of 7. And yet I know that I can reach this node here with a maximum cost of 3. Why 3? Because somewhere, this edge here had a cost of 3, and this one had a cost of 2 and a cost of 1. So the minimax cost to reach this node in this upper left corner is 3. And it's not going to get any cheaper by me adding an edge of weight 7. But I will add this one, and I will add that one. And at this point, I have added n-1 edges, and I know I can stop, because I already have a spanning tree. So this is the minimum spanning tree, and it induces a cut. So it induces a cut in my image, like so. And then I'm going to say that, well, these here are going to be, it's going to be the blue region because it's connected to the blue seed. And these pixels here are going to be the green region because they're connected to the green seed. And I have segmented my image into a foreground and a background region, much as you have seen in this demo earlier. So this is the seeded watershed segmentation algorithm. There is also something called just watershed segmentation, and this is the same thing, except the seeds are generated automatically. Where automatically means that in this case the local minima are used as the seeds. Now more in detail, there is a node-weighted watershed algorithm and there is an edge-weighted watershed algorithm, but the basic, well, it's maybe easiest to explain for the node-weighted. For the node-weighted watershed algorithm, you can think of the image as a topographic surface, so something with valleys and mountains, and each local minimum you would declare as this is one seed. So you just find all the local minima first, and then you run seeded watershed segmentation using these local minima. Typically, this will give you a zillion tiny regions, especially if the image is noisy. Then you will have many local minima, and then there are all kinds of more or less heuristic strategies to simplify this hierarchy. If you think of the dendrogram, to cut it at a somewhat higher level, etc. Now, in the application which I mentioned when we started this morning, there the seeds were not given by a human user, but the seeds were found. So in this case, the seeds were each nucleus of a cell in microscopic image became one seed, and here the nuclei were found, or the seeds were found by some deep learning method, namely by stardist. Good. So this is seeded watershed segmentation and watershed segmentation, and I want to show these in real life in terms of the elastik program. So if you go to download, you can on one hand find the program, and on the other hand, if you scroll way down, you can find example data. And I have downloaded this data from the FlyEM project, and but I've not, beyond downloading, I've not done anything else. And then I want to walk you through a seeded watershed segmentation example. In this elastik program, there are various workflows, and one of them is called carving. Why? Because a biologist, intended user, may not have heard of seeded watershed, and so we were looking for a perhaps more intuitive term. All right, I'm creating a project. And now I'm adding data. So I add a single 3D or 4D volume from a sequence of images. I'm going to select a whole directory, namely this directory in which I had downloaded all the images. And then I need to specify, do I want to stack across time, or across a third dimension, or across spectral channels. I want to stack them across the third dimension. Pressing OK, and it now has assembled a 3D volume out of these many 2D images. And here we see three ortho views of this small data set. So these are three orthogonal views. And if I show these crosshair cursors, then, for example, here, as I move around here, you see that the blue line down there moves, and this shows you where this image is located in this other projection here. Good, so this is just the raw data, and what are we looking at? We're looking at focused ion beam scanning electron microscopic image of a neural pill, so an insect brain. And you see here all these thin neural processes, some thin, some thick. We see mitochondria. We see, I think this would be a T-bar, so the synapse of an insect, and so on. And let's say we want to now look at some of these objects here. then there is a pre-processing stage in which I can specify first, what's the boundary indicator here? Are the boundaries shown by bright lines, or are they shown by dark lines, or by step edges? They are shown by dark lines. I have two options here. For dark lines, I could compute it on the smoothed image or on the original image. I'm just going to use here the original image and press run. And what it now does is, well, it uses the standard watershed algorithm. So it first tries and find dark lines in the image. Let me show this to you. So this was the raw data. Then this was the filter that was used to bring out or to emphasize the boundaries. So there was a question earlier, what does the y-axis mean in the graph that I showed? Well, this would be the graph that we use, and it's whatever method you want to use, it should only somehow emphasize boundaries, which this one does. And what does it do? I think the tooltip there said something about it will invert the image, then compute the Hessian, compute the largest eigenvalue, and so on. So this is some standard image processing routine, not a deep network in this case, which creates this thing. And now all the local minima are found, and there are zillions. And then with this height map and those local minima, a seeded watershed transform is being computed. And this is the result, which is a coarse graining of the original data. So these are called superpixels. And instead of dealing with millions of pixels, we only have to deal with tens of thousands of superpixels. So these superpixels, each one has a size of whatever. Is it 10 by 10 by 10? So that would mean each superpixel here, on average, would comprise 1,000 pixels. And that means, of course, that this is, a reduction of the number of things I have to deal with by a factor of 1,000, which is nice. Now, what's really important is that these superpixels, they should stay inside the pure segments. So it would be bad for a superpixel to actually connect two distinct segments. But these look okay, so I can now move to the labeling stage. And what happens now is just a seeded watershed computation where I'm going to give the seeds. So I'm clicking, for example, let's say on this object here, and I'm clicking on this background. And then I press segment, and I get out, this thing here in 3D, and then I can, study. Does it look okay? Do I spot any errors? For example, here, this should also have been part of the object. So I'm putting also a blue seed here. I'm pressing segment again, and yeah, it has repaired this tiny hole. Okay, so that looks reasonable. And now you can do this for any number of segments. There's one interesting tweaking parameter here, namely, I put one seed inside and one seed outside, and a priori, you would expect that I thus partition my volume into two halves. One half would be associated with the foreground, the other half would be associated with the background. But you see that really the foreground object only filled a small part. And the reason is that we've introduced a little bit of a bias here. a bias in favor of the background. I can increase this bias, like so. You see now the background grew much more aggressively than the foreground, and this thing has shrunk to almost nothing. Or I can make the bias very small. So I take something close to 1. Yeah, actually, that still did not bleed out. Okay, I'm putting in 1. Still seemed reasonable. Yeah, but if you should try this yourself, if you pick another segment, I want to clear all brush strokes. If we pick another segment, we will see that, let's say like this one and this one. Let's see what happens. Yeah. Yes, I would say now it really has been bleeding out of this desired segment because the foreground has grown as aggressively as the background. Let's see if we can fix this here. Yeah, okay, so you see this is a really important parameter to play with. Okay, and so you can here carve out objects one by one, and this is useful, for example, to generate ground truth, to then train deep neural networks, etc. Okay, so we've here seen the watershed algorithm, which gave us the superpixels. And we have seen the seeded watershed algorithm based on those annotations that I gave in action. And by the way, this seeded watershed propagation here did not happen on the level of pixels, because this would have, this would become slow, especially if you work with larger 3D images. But instead, based on these superpixels here, we built a region adjacency graph. So each superpixel becomes one node in a graph. And then on this graph, which is no longer nicely Cartesian structured, but has an irregular structure, on this graph, then the seeded watershed computation is performed. All right, a couple of comments here. So seeded segmentation behaves very differently depending on whether we use shortest path or whether we use minimax path. And I tried to indicate it earlier by this picture here with the thin, long object. Okay, let me continue the object here all the way to the boundary. Good. And I was saying earlier that if I use shortest path with this seed and with that seed, then especially when there is noise in my boundary information, and you have seen that in real life the boundary information is never perfect, but it looks more something like this. Yeah? So even inside an object, ideally it should be completely black, but even inside an object not completely black, we still have this little bit of boundariness here. This is why I'm pretty sure that the resulting segmentation, when we use shortest path, it would not grow all the way until the top of the image as we desire. Now, on the other hand, if we use the widest path computation, it will run until the end here with no problem, as you've just seen in my demo, but there's a tiny gap in the boundary, and it's going to bleed out here, and it's going to eat away at the region which should really belong to this other annotation. So both have their advantages and limitations that I've tried to put into words here. And which one is better really depends on the nature of the imaging data that you're looking at. And so far I mentioned shortest path and minimax path. There is another really important distance measure, namely the resistance distance, which uses the concept of random walkers or of Markov processes to estimate distances between points, and that behaves yet differently again. And it's even possible to some extent to interpolate between these extremes and to tune your algorithm to which of the limiting cases you would really like to see. Good. Let me know if you have any questions.